about climate change and its, or at least possible effects or reduction of the effects of climate change from a geologic perspective. This is something that she's been working on also as her PhD at Columbia University, and before that in 2006 she graduated at the University of Southern California and has since then moved on to Columbia, but she also has a joint position, not just with CSU Sacramento, where she is now, but also with the U.S. Department of Energy National Energy Technology Laboratory. So she's got dual appointments, and we're very fortunate to have her here as an expert to talk about this, to link climate and geology together. So it's a perfect match for our department and to appeal to a wide group of audience here. So with that, I will try to get this going. I think I can do it. Let's see. Component.
Get up there, Bill.
Yeah. Oh, there we go. Just going to press a little more. Great. With that, I'll give it to Dr. Amelia Vankeuren.
All right. Thank you for having me. It's nice to be part of such a illustrious set of speakers you've got coming up here. I don't need to drive up more often. So today I'll be talking about some work that I started in my PhD, and we're continuing looking at how to combat climate change using mantle rocks. So on my first slide here is a picture from the Sultanate of Oman. This is the Oman Ophiolite. So it's mantle rocks that have been thrust up onto the continent, and these rocks are reacting with precipitation and dissolved carbon, and they are forming carbonate minerals. So these really pretty white waterfall looking things into blue pools are in fact carbon dioxide that was in the air, has been pulled out and sequestered in the form of minerals. So we use this site as a natural analog for geological storage in mantle rocks to see if we can figure out a way to speed up the process and get nature to sequester more of our carbon. I'd like to briefly acknowledge my co-authors, who are also my PhD advisors, collaborators in Oman, like the Ministry of Water Resources and Geological Survey, and funding sources, mostly NSF. All right, as we go on this journey to the Oman Ophiolite, I'd like you to meet the tour guides, the local camels. They know these mountains better than anyone else, with the possible exception of the wild donkeys and the goat herds, but we're going to see them along our trek today. All right, so the talk is divided into 3 parts. We're first going to look briefly at the need to reduce CO2 emissions using carbon capture and storage, then look specifically at mineral carbonation as a natural solution for sequestering carbon, and then finally hone in on the Oman Ophiolite as a natural analog. All right, so you guys are geology and environmental studies majors, so you already know climate change is one of the preeminent global challenges facing us today. The question is what to do about it. So we've got CO2 coming out of transportation sources, energy production, industry, but what can we do? Also, the effects are pretty dramatic. The drought here in California, 5-year historic drought, 20% of that was probably contributed by climate change. The most recent hurricanes in the south, the destructive damage of those storms, also potentially due to climate change. Food insecurity, heat waves, water scarcity, all of these are effects of climate change. Again, how do we mitigate those? All right, so here in the US, where we have already extensive energy use, people might say, in order to reduce carbon emissions, why can't we just conserve? Let's be more efficient. And in the US, that's certainly a possibility. This is a graph showing per capita energy use over time. Here we are, the US, way at the top. Most of the Western European countries, France, Germany, at about half our per capita energy use. And then the global average down at half of that value. So in the US, yeah, we can probably bring our energy consumption down to Western European levels and still maintain a high standard of living. But over the next century, the developing world is going to try to increase their standard of living, which is going to increase energy use. So even if we are more efficient, globally, there's going to be a higher energy demand. And if we just bring the current global population up to a European standard of living, we're going to double our energy use. That's with no population increase, which of course is projected to occur. So just lowering energy demand is not an option. And renewable energy like solar and wind and geothermal are great options down the road to reduce our carbon footprint, but we can't just flip a switch and have our energy consumption go from primarily fossil fuel to primarily renewable. So this is from 2014. This is a global energy supply pie chart, and you can see that fossil fuels account for over 80% of our current global energy supply. Where renewables, what we think of as the classic renewables, solar, wind, geothermal, are only about 1.5%. So in order to ramp up those renewable energy to supplant fossil fuels, it's going to take a while. We can't just do it overnight. So in the meantime, we'd like to find a way to reduce the carbon footprint and still be able to generate energy. So in order to reduce the carbon footprint of our energy source, there's been a number of ideas on how to do this. This one is put forth by the International Energy Agency. And we're looking at a plot of the global emissions of carbon dioxide by year, projected out to 2050. And if we just continue emitting business as usual, don't try to change anything, then the curve would go up to over 60 gigatons a year. And this is, in fact, an old figure. It would be even more now. So what we want to do is get down to global emissions of close to zero. So one option is to combine a lot of different wedges. Each of these little wedges brings down the carbon emissions by so much. So a lot of these are efficiency, fuel efficiency, electricity efficiency. These are low-hanging fruits where you can easily switch. May involve some capital investment, but you might save money in the long term, like changing your incandescent lights to LED. The LED costs more, but your energy savings more than make up for it. Then we have increased use of renewables. That's this orange wedge here. Increased use of nuclear power, which after the Fukushima disaster is a little more sensitive. And then at the top here we have carbon capture and storage. So the first takeaway I want you to have from this talk is that there is no silver bullet. There is no one solution that's going to save us from climate change. It's going to take all the tools we have in the toolbox. So for the rest of the talk, we're going to focus in on carbon capture and storage as one of those potential tools. So carbon capture and storage is a way of decarbonizing fossil fuel energy. So we still burn coal or natural gas, but instead of letting the carbon dioxide just go into the atmosphere, we put a lid on that power plant and capture the carbon and then transport it and store it somewhere, hopefully permanently. So instead of just emitting the carbon dioxide into the atmosphere, it is kept out of the atmosphere and doesn't impact the planet. So one option is capping the power plants. Another is actually pulling carbon dioxide out of general air. So it's a lot more dilute. It's only 400 parts per million instead of 10%. So it's more difficult, potentially more expensive, but you could do it anywhere. You could remove carbon dioxide from the air anywhere instead of having to be at a power plant. And you could use it to potentially get negative emissions. So later on down the road, once we've totally decarbonized our energy supply and we find that we're at 600 parts per million carbon dioxide and this is really not a comfortable place to be, maybe we can still remove carbon dioxide from the atmosphere and try to get the planet back to a more natural state. All right, so when we talk about carbon storage, geological carbon storage, mostly people think about injecting carbon dioxide into a saline aquifer for long-term storage. And this is a technique that has been proven over many years. This is the Sleipner field in Norway. It's a natural gas field. And the natural gas has about 10% carbon dioxide. So the gas field has been producing for decades. In 1995, Norway put a $50 a ton tax on carbon dioxide, and the Sleipner field said, hey, we don't want to pay that, let's instead separate off the carbon and inject it back underground. So that's what they do. So they bring up their mixture of natural gas and CO2, they send the natural gas off for, the natural gas goes off for sale, and the CO2 gets stored back underground. So they've been doing this since 1995. So for over 20 years, they've been injecting a megaton of carbon into the saline aquifer beneath the sea surface, and it has been functioning successfully. But this requires long-term monitoring, because CO2 is buoyant relative to water. It's trying to rise up out of there. So if there were, say, a fault going through an impermeable layer that's keeping the CO2 down there, that CO2 could escape. That's not helpful. The CO2 gets back into the atmosphere. Now we have climate change again. So you have to monitor it over the long term to make sure that your CO2 is staying where you put it. So in Norway, they've been doing with seismic. This is both a map view, so you can see the lateral plume extend as the CO2 is injected under the subsurface, and it's spreading out under that layer. And in 3D, you can see a vertical cross-section here of that CO2 bubble under there getting bigger and dissolving into the saline water down there. So the CO2 is indeed staying where it's supposed to in this field site. But you have to monitor this for decades to centuries to make sure that the CO2 doesn't ever escape, which could be very expensive. So we're looking at another option for CO2 storage that would not require long-term monitoring, and that's mineral carbonation. So mineral carbonation is turning gaseous CO2 into a carbonate mineral, like limestone or magnesite. And to do that, you need silicate rock feedstock that has divalent cations like magnesium and calcium to combine with the CO2 to form your carbonate minerals. And this is in fact how the Earth regulates its CO2 in the atmosphere. So historically, in geologic time, when you get increased concentration of CO2 in the atmosphere, you then get increased weathering rates because the rainwater becomes more acidic. You get more release of these divalent cations, more carbonate formation that draws down the CO2 in the atmosphere, and then you get less weathering, so it's a nice little balancing feedback. The problem is that Earth does this on a hundreds of thousands of year timescale, and we're putting out carbon dioxide more and more every year. So can we speed up this natural process? So let's first look at how it works. Mineralization takes 3 steps. First, we need to dissolve the CO2. So we start with gaseous CO2, turn it into a carbonate ion. This is like a fizzy water or a soda. When you pop that lid and you hear the psh sound, that's your dissolved CO2 escaping, because that one's been pressurized, but some amount stays in there. So we're trying to get our CO2 bubbles to dissolve into the water, and then dissolve a silicate rock. So olivine and pyroxene are great rocks for this. They have a high cation, so magnesium or calcium ratio to the rest of the rock. So more of what we want per unit rock. So as we dissolve this rock, we get magnesium and calcium ions, and then these ions combine with the dissolved carbon to form carbonate minerals. So things like limestone. Limestone is thermodynamically stable at the Earth's surface. It's already very common in nature. It's even used as building materials. So there's the potential for beneficial uses of limestone. So it would be a nice permanent way to store the CO2 that would not require long-term monitoring to make sure it escapes, because once you form the limestone, you've got a rock, it's not going anywhere. Okay, so said we want to speed up the natural process. There's a couple ways of doing this. The first is to increase the reactive surface area. In the same way that when you brew a pot of coffee, you don't throw in whole beans, right? You put it in the grinder, you make the size much smaller, the particles then have a higher reactive surface area, and when you put your coffee grounds into your coffee pot, you can brew a nice cup of joe. If you put just the beans in, it would be pretty weak. Okay, so we could increase reactive surface area. The other way we could speed up reaction kinetics is to heat the system up. Heat causes particles to move faster, it increases chemical reaction kinetics. If you think about sun tea, you put your tea bags in your tea, or in your water, you put it out on your porch and you let it sit for several hours. If you instead boil water and pour it on your tea bag, you have tea in a couple minutes. So, same concept for reacting the rocks. If we add heat, the reaction goes faster, we can sequester more carbon. So if we're looking to do this for mineral carbonation, this would mean mining the rocks, trucking them somewhere where they can be ground into smaller bits, then putting them in heated, pressurized vessels to increase the heat and the reaction kinetics. And all of this is very energy intensive and makes it potentially not useful. So if you're using this method to speed up your CO2 sequestration, but then it takes 50% more power to drive this process with the mining and the grinding and the heating, then you have to burn 50% more coal, which means you have more to sequester, and it becomes less of a benefit. So, what if instead of taking the rock to the CO2, we take the CO2 to the rock? So what I've just described is known as ex situ mineral carbonation. My group looks at in situ mineral carbonation, so injecting CO2 directly into a rock formation. The location we're looking at doing this is an ophiolite, because ophiolites are very reactive at the Earth's surface. They are mantle rock, so they're used to being at depth under high temperature and high pressure conditions. Then when you have a tectonic collision that brings them up to the surface, now they're under low pressure, low temperature, they're not in equilibrium with their system, and they dissolve relatively quickly. So ophiolites are great locations to find these magnesium silicate rocks that easily react. And they are globally distributed. So this is a map showing the location of ophiolites. All of these little red dots are ophiolites. The Oman Ophiolite is sufficient to sequester 30 trillion tons of carbon dioxide. That's 1,000 years worth of anthropogenic CO2 output, if we could get the entire thing to react. Globally, there's enough to sequester 100 trillion tons of CO2. And in the US, we also have extensive ophiolites, so here we are. And both on the west coast and east coast, we have ophiolites. We have actually almost as much as Oman. It's just more distributed instead of being in one giant lump. Okay, so ophiolites could potentially take up a lot of CO2. But will they? So now we're going to look a little more specifically at CO2 storage in the Oman Ophiolite. So here's a map in case anyone doesn't know where Oman is. It's on the Arabian Peninsula next to Saudi Arabia and Yemen. And they actually control a piece of the Straits of Hormuz, so they are a geopolitically important country. That's where the oil gets through for the Persian Gulf. And there's a mountain range in the northern part of Oman that is almost entirely ophiolite. So here's a grossly simplified geologic map of northern Oman, and these pink blotches are peridotite, that mantle rock in the Oman Ophiolite. So this is the largest ophiolite in the world. It's also a great field site because conveniently it's in the desert. You don't have all those pesky plants on your rocks. Okay, so the Oman Ophiolite is naturally carbonating, which we'll explore in a minute. But criticism that people have had for in situ mineral carbonation, where we're trying to carbonate minerals in the formation, is that these rocks are fractured rocks. They are not nice sandstones with high porosity and permeability. All of their porosity and permeability, pretty much, is in fractures. So the carbonation process involves a volume increase of about 80%. So you're almost doubling your volume, which means that you could potentially fill up your fractures, and then you can't get any more CO2 down there, and you're done. That's it. But the other option is that as these fractures fill up, the minerals actually exert pressure on the rocks around them, and they cause reactive cracking. So they could actually break the rocks and create new porosity and permeability. In which case, it wouldn't clog up, and we could get at more of the peridotite and potentially sequester significant volumes.
So you're going to use fracking to solve your...
So that's one option. We're actually hoping that nature is going to do it for us. So nature actually shows us that it is possible for these systems to carbonate for long periods of time. This is an image of a Carbonate Terrace. So this is all recent limestone with veins feeding it from the subsurface. And we've done carbon dating on this terrace and veins. And we've got dates ranging from carbonate that you can see forming right now to 50,000 years old to ones that are too old to date, at least using carbon dating. So it looks like this system has been active for at least the last 50,000 years. So it hasn't clogged and shifted to some other location. There are also locations in Oman where you have entirely carbonated peridotite. So over here is a picture of a mountain in Oman with these sections of listvanite. That is peridotite that has been entirely carbonated. So every magnesium ion that was in the peridotite is now carbonate. And there's a whole mountain of this. So given the right conditions, naturally, this was able to come to full carbonation. So it is possible. Then the question becomes, what conditions are necessary in order to fully carbonate the peridotite? And again, can we do it on a human timescale? So when we look at that natural system, we see that it is fully carbonated. We want to know, how did it get there? Like this goat in a tree, they're all over Oman. I still don't understand how they climb trees with their little cloven hooves, but there they are. So we're going to look at the natural system. How does that natural carbonation process work? At what time scale does it operate? And can we enhance the system to take up significant amounts of CO2? So looking at the first question, how does that natural process work? First thing we had to do was study it. So here's my team. I say my team. At this point, I was a PhD student. So I was a junior member of the team, but that's okay. Field sampling in Oman. So we were taking water samples, samples of this recently formed carbonate mineral. This is an older Carbonate Terrace. And looking at the water chemistry and how it changes from shallow to deep. We also did some well sampling. This is me sampling a borehole that is 300 meters deep with a baler, which meant that I had to feed it down and then bring it back up full of water from 300 meters. Definitely didn't need to go to the gym that month. And then here we are, helped by our trusty camels once again. Okay, so we took water samples, we did aquifer testing in the peridotite to try to get a sense of permeability, we looked at carbonates, and then we put it all together to get a nice story for what's going on. And this natural carbonation process has actually been looked at since the late 60s in Oman and in California. So the natural system starts with recharge to a shallow aquifer. We've got precipitation coming in with carbon dioxide dissolved in. That dissolved carbon dioxide and slight acidity to the water dissolves the peridotite and gives us some magnesium ions, which produce a type 1 pH 8 to 9 water that's magnesium and bicarbonate rich. So this is in the shallow subsurface where the water can still communicate with the atmosphere. And this produces shallow carbonate veins. Then when that water infiltrates deeper into the aquifer where it's cut off from the atmosphere, there's no more carbon supply, which means that there's no more carbonation once that gets precipitated out. And the system switches to low temperature serpentinization. So we are taking that olivine, essentially hydrating it to produce serpentine, and in the process we exclude calcium ions. So the water becomes pH 11 or 12, high calcium concentration, high hydroxide concentration. So this water has very little dissolved carbon, high calcium, high pH. When it comes back up to the surface, it's hungry. And when it gets access to dissolved carbon, it starts sucking that carbon into the water. That starts to lower the pH. It also allows it to then precipitate calcium carbonate. So we've got limestone forming at the surface. And that's what forms those really nice blue pools, because the water comes out, sucks in carbon dioxide from the atmosphere, forms carbonate minerals that are white, makes a nice backdrop for the blue pool. And the amazing thing about this system is in geologic time, this carbonation is happening in the blink of an eye. It's so fast. So this is actually a scum of carbonate sitting on the top of a pool. So where the water atmosphere boundary is, you're getting dissolution of carbon dioxide into the water, formation of carbonate minerals, forms a film on the top of it, and then until something knocks it off, you have limited transfer, so it takes a while to form more scum. But if you knock this stuff off, or you sample it, and you come back 2 days later, the scum is back in place. So these are minerals forming in real time. And that was atmospheric carbon dioxide, now stored as this carbonate film. Another cool thing we found is that the peridotite is still actively serpentinizing. So a lot of people think of serpentinization as happening mostly at high temperature, like under the ocean floor, but it is in fact ongoing here, and we can tell because we have hydrogen in some of the wells. So this serpentinization process generates hydrogen gas, and then in some wells that's then converted to methane. So this got the biologists excited because hydrogen is thought to be what fed early life on Earth. So before we had oxygen in the atmosphere, before we had photosynthesis, we had chemosynthesis at the ocean vents, and that's fed by the hydrogen produced from serpentinization. And so these weird worms are getting their energy from the chemical energy available down there. And it produces carbonate towers. So, has anyone heard of Lost City? A couple of the professors. All right, so Lost City is carbonate towers formed at a vent on the ocean floor. So you've got seawater going down into the ocean crust, serpentinizing, come back up, again, high pH. When it mixes with the seawater, you get the formation of these gorgeous carbonate towers. And the ones in Lost City are up to 60 meters high. So these are enormous carbonate towers. Yeah?
So you're saying you're releasing methane by this process again, or is there some bacteria who use the methane
There's bacteria that are using it.
So, because otherwise you have another problem.
Right. Well, and yeah, so we're not going to get into the methane release from natural processes. Yeah, that could seriously be contributing, but yeah, nothing we can do about that. Besides, it's probably getting... Okay, so we've got a good handle on the natural system, at least how it works. Now the next question is, what time scale does it operate at? So how quickly is it putting away carbon? And one way to constrain that is to try to figure out the age of the groundwater. So we took water samples and did tritium dating, and we tried to do carbon dating, and then we used some noble gases to look at recharge temperatures. Because we want to know, like this baby camel, how old is it? How old is the water? How long does it take the water to reach pH 11 or 12? And our results showed that that type 1 pH 8 or 9 magnesium bicarbonate water can form in 40 years, but the pH 11 or 12 calcium hydroxide water, we don't really know. So it's tritium dead, which means that it's older than 60 years. Our attempts to carbon date it failed because it's so carbon depleted that there wasn't enough to date in a regular size sample. And it's easily contaminated by atmospheric carbon because that water is so hungry, so high pH, that if you get just the smidgen of exposure to the atmosphere, it sucks up modern carbon, and then it looks like it has a modern carbon age, but is tritium dead, which is not possible. So, we then looked at relative age indicators. We looked at accumulation of helium from uranium and thorium decay. Those pH 11 waters do have a lot more helium, so they are older. And some of them actually showed a recharge temperature 7 degrees cooler than Oman is right now. So that now lines up with the last glacial maximum. So those waters are potentially more than 15,000 years old. But other than that, we can't say. So,
how do you do carbon dating in non-biogenic carbon?
I don't know the exact process, but the Woods Hole carbon dating system somehow does it. I mean, you have to do corrections because you can have potential effects if you, say, dissolve carbon that's really old from your rocks, then that would make your sample look older than it should be. So there are processes that can affect the inorganic carbon, which makes it more complicated, but you can still do it. Okay, so we don't know how old that water is. We've hit a roadblock. So now it's time to turn to less field-intensive methods, and we're going to do a little modeling. Okay, so I set up a reaction path model that looks at rainwater infiltrating into an open system of peridotite, so it's reacting with the rock, but can also interact with the atmosphere, and then that water going into a closed system where it's cut off, and just trying to get the chemistry of the model to match what we see in the field. So I validated the model. Looks like the model reaction path matches what we see in magnesium and calcium concentrations, so that's great, because you can get a model to say just about anything you want, but you want it to actually describe the natural system. So here, in fact, we see a decrease in magnesium going from the open system to the closed as you carbonate the last remaining dissolved carbon and then start making serpentine, and an increase in calcium as the calcium is excluded from serpentine and accumulates in the water. Okay, so the model matches. So we're going to say that it has useful things to say. And one of the things we wanted to look at is how long does carbonation proceed naturally? So this is showing CO2 stored as carbonate minerals over time, and we have an increase until about year 500, and then it flatlines. There's no added carbon storage. And the model took about 6,500 years to reach pH 12. So based on mineral kinetics, that's how old we might expect that type 2 really hyperalkaline water to be. And we stopped carbonating when it ran out of carbon dioxide, which was at about year 500. So there were 6,000 years where the water was reacting with the rock, but not doing anything useful as far as carbon storage. So the system is carbon limited, which means that if we can add more carbon, we can potentially create more mineralization. Okay, so now we're going to look at, can we enhance the system to take up more CO2? Or how fast can we get it to go? Like these racing camels. Okay, so now we take the same model that we had before, but instead of just having the natural water go from the open system to deeper, we're going to add some carbon dioxide. So we're equilibrating the water with 100 bars carbon dioxide, equivalent to injecting carbon dioxide at depth, and seeing what happens. So if we go back to our conceptual model of the system, I started by just putting CO2 at about 1 kilometer down, so lower temperature than deeper. And you get an increase in carbonation of about 200 times. So that's good. Then if we go down to the temperature at about 2 kilometers, we add some heat from the geothermal gradient and put our CO2 down there, and now we get 16,000 times more carbonation. So that's even more promising. Although the natural system is probably putting away something like 40,000 tons of CO2 a year, we'd really like it to be putting away millions of tons of CO2, or potentially gigatons of CO2. So 16,000 may or may not be enough. So the other issue is that this model was essentially taking a parcel of water, having it react with some rock, and then moving on to another chunk of rock in sort of a 1D, not very realistic scenario that couldn't model things like, are those fractures clogging up? So now we're going to go to a slightly more complicated model where we can look at those constraints and see if the system is potentially going to continue, or if it would carbonate very quickly but then be clogged and done. So for this model, I used a reactive transport. So we've got CO2 injection into a 3D setup, and there's a fault here just to see what would happen if we had a potential leakage scenario. So we're injecting dissolved CO2 and flowing it through a peridotite system. And that peridotite is divided into 3 separate continua. So we've got big fractures like we see in the peridotite. You can see them with your naked eye. They're all over this place. Nice, pretty rectangular 90-degree fractures. Then also in the peridotite we have micro cracks. So due to serpentinization, there are cracks on the 10 micron scale. So every 10 microns you have another itty bitty tiny crack. So these could potentially add a high reactive surface area if you get flow through these micro cracks. And then the matrix rock itself, which is relatively impermeable and very low porosity, so lower reactivity. And I tested this model looking at sensitivity to 3 different parameters. We've got a couple different ways of increasing reaction rate, right? We've got temperature, so looked at 2 different temperatures, a lower and a higher. Then the reactive surface area, looking at a geometric reactive surface area based on fracture spacing, and then a conservative one that was calibrated to serpentinization rates seen in places like Lost City. And then 3 different permeabilities, because we don't really know the permeability at 2 kilometers depth in this location. We don't have a borehole going down that far. So taking kind of a high to expected to low range permeability for those depths based on crustal permeability curves. And the results show that you do have continued carbonation in all of the scenarios. There's a very slight increase for all of the ones down here. But there's one model where there was significantly more carbonation than any of the others. So this one just took off and was still continuing at a good clip 50 years down the road, so it looks like it did not clog up. So we're going to look a little more closely at this one that worked well. And that was at 2.5 kilometers down, so the higher temperature with the expected permeability and the higher reactive surface area. So if we look at the model results, this is looking at the carbonation efficiency. So there are areas where parts of the model were pretty well carbonated. That's a carbonation efficiency of 1. That's every magnesium ion getting turned into carbonate minerals. But it really varies depending on where you are relative to that injection site. So right close to the injection site, you have dissolution. So these are minerals dissolved or precipitated. Anything below this line is dissolved, above is precipitated. So we have olivine dissolution and a little bit of serpentinization, but no carbonate minerals forming. That's because you're still in a really low pH zone. That's right where you injected the CO2. Now, as that CO2 starts to dissolve peridotite, it buffers the pH, it adds magnesium to react with the CO2, and you start getting carbonate formation. So this here is magnesite precipitation. So we've got peridotite dissolved, some serpentine forming, and carbonation. Then if we step farther out, the carbon got depleted from the water before it gets to this location, so now we're back to only serpentinization with no carbonation. So there's kind of a front of carbonation progressing from close to the injection well and stepping out as it carbonates the rock behind it. Then the carbon gets farther out, and so you're gradually carbonating this chunk of rock. So that's good, that's promising. It didn't clog, and you're getting carbon progressively farther out into new rock. The total carbonation rate depended a lot on the relationship between the flow rate and the reaction rate. So in some scenarios where we had a really low flow rate because we had a low permeability, you just couldn't get much carbon down there. So the carbon that went down got turned into carbonate minerals, but there just wasn't enough to have a big impact. Then, if you increase the flow rate significantly, use the high end of the permeability curve, the flow rate is too fast, and now you're flooding the aquifer with pH 2.5 water, which, first of all, is not great for environmental reasons, and second of all, it's kind of a waste because you're pumping a lot of CO2 down there, but it's going by the rock too fast for it to react and form carbonate minerals, because you need the minerals to dissolve and create that pH buffering. So when you get sort of an intermediate, a more balanced flow rate to reaction rate, you get a little more carbonation, and then we get this one sweet spot where carbonation proceeds much more quickly than in the other models. And these all ran to 50 years, because we figured that was a reasonable time frame for an injection scenario. And I calculated the cost if we were to inject carbon using this kind of a scenario where we're dissolving it into water and then injecting it down. The nice thing, if you dissolve it into water, you don't have to worry about the buoyancy effect. It's not going to leak out, but then you have to pump more water down. And I calculated it at $6 a ton. So this includes the cost of pressurizing your CO2, pumping it down. It does not include the capture or the transport to a location, because those are going to be the same for a traditional geologic CO2 storage. And that conventional one is estimated at between 50 cents and $12 a ton. So the cost of mineral carbonation is somewhere in the middle of that. But with the mineral carbonation, you wouldn't have to do that long-term monitoring, which could potentially be much more expensive. And that monitoring is not included in the cost of conventional CO2 storage. Okay, is it actually practical to get CO2 to ophiolites? Well, if we look at California, this is a map of CO2 sources. These blue dots are energy producing locations that are emitting CO2. And here I've overlaid maps of ophiolites. These little black dots up here are ophiolites. So we've got Mount Diablo is got some ophiolitic rock near carbon source. So there are some locations where CO2 is close to your reactive ophiolitic rocks. Whether or not people want to be injecting CO2 into these rocks is another matter, but logistically it could be possible. So there are still open questions. Things like what actually is the permeability and reactive surface area at depth? We've just used estimates based on available literature, but it would be great if we could actually quantify those. Maybe do a pilot project and see if carbonation does continue if we inject CO2 down there. Yeah, so see if the model actually really does capture what the natural system is doing. And then also, what is the groundwater age? So we had the model say it was 6,500 years, but it would be great if we could actually constrain that. And I'm actually trying to get some funding to go and do argon dating on the groundwater so we could maybe get groundwater age, and then we constrain our reactive surface area, and then that would help better our predictions for how much CO2 we could put down there. So, just to summarize the conclusions, we've got type 1 magnesium bicarbonate water doing shallow carbonation, taking about 40 years to form. Type 2 high pH 11 or 12 water forming in some amount of time, maybe 6,500 years based on modeling. The natural system is carbon limited, which suggests that if we add carbon, you could sequester more. And injecting CO2 would rapidly increase carbonation and increase carbon efficiency, so we could convert more of those magnesium ions to magnesium carbonate. But we need to find that sweet spot for the flow rate relative to the reaction rate in order to take most advantage of the peridotite that's down there. And that's it. Well, I'm happy to take any questions.
Great talk, thank you. Question is, thinking about, so this works, but now the next step for applying it across the world, wherever you're going to do it. And so geothermal gradient is going to be an important aspect for the deep injection. And that's going to differ by the tectonic setting.
Yep.
And also, I was thinking back to the chart, I hadn't seen one like this, cool about the, that the US is using so much per capita. But then you think about the actual population numbers.
Right.
And so trying to take these effects of the actual tectonic setting of an ancient ophiolite combined with a fossil fuel production facility, or, well, I guess not even that, just a geothermal gradient, I guess. And if it's being captured, where would you want to, if you could get the money to set up an experiment other than Oman, in more developed area, where would you do it?
I haven't looked that much at other locations that would be ideal. Oman is nice because there are locations where on top of the ophiolite you've got a carbonate caprock. So if you were to potentially have some escape of CO2, you would have a location to trap it. There's big ophiolites. I mean, California would be nice because it's convenient, but I imagine that permitting issues might be a problem. Like New Caledonia and Cyprus also have big ophiolites that could potentially be used. Yeah, but for a pilot project, I think Oman is probably one of the best characterized ophiolites, and that would be the place to go. Yeah.
So you open your talk of saying it would be nice to sequester everywhere around the world more or less CO2,
Yeah.
and not bringing it to a system. So Oman, for example, doesn't have a lot of industry around the ophiolite, so you have to bring it from far away. California is better, but then you still have a lot of cars to produce CO2, so it's very difficult to do that. And so when I think about, even if you have all the infrastructure available that you could actually bring this there, how quick would that have an effect?
How would it have an effect?
To draw down CO2 from the atmosphere, period, or doesn't or stop the increase.
A timeline?
Yes.
Well, I mean, for a timeline, first we need to do pilot projects to see if this kind of thing even works.
Yes.
But I think for places like Oman, where you don't have huge CO2 sources, I think they put out something like 64 million tons of CO2 a year. That's where air capture would be really great. So people like Klaus Lochner out at Arizona State have developed resins that CO2 absorbs to, and then you just get the resin wet and it releases it, and then you can compress it. And so ideally, then Oman, if they are storing more CO2 than they're putting out, they could start selling those CO2 credits if CO2 were actually worth enough to make it worthwhile. But as far as getting it ramped up to have a significant impact, I think that's really going to depend on the political will. I think if there were a significant price on carbon, then you find a way to do it, right? I mean, Norway started injecting CO2 in Sleipner pretty quickly after they put the tax on there. So it's just a matter of the incentives. And there are locations where they're doing pilot projects in basalt. So like in Iceland, there's also reactive rocks. It's basaltic glass, lots of magnesium and calcium. And they've got a power plant that also had some natural CO2 in it. It's a geothermal plant. And they're injecting CO2 down in there. Basalt is more permeable, so it's easier to flow through. And it looks like that is being a successful pilot project. So there's other options for in situ mineral carbonation too. Sandrine? Yeah.
Back to the process.
Mm-hmm.
So if you, let's assume the process, if you consider the process, do you have to worry about running out of type 2 water? Since this is old water, that's taken a long time to produce.
Yeah, so the CO2 injection process actually doesn't rely on the type 2 water. So the surface carbonation does, like with a naturally where it flows up and sucks CO2 out of the atmosphere. But if you just inject CO2 into the subsurface, the acid in the water directly starts dissolving the peridotite, and the magnesium that is released from the peridotite reacts with the dissolved CO2 and forms the carbonate.
Yeah,
so
your limiting region is more the rock than the water.
Yes, yeah. So yeah.
Cool.
Yeah.
Why the range in estimates on costs of injecting in Sleipner formation?
Oh, you mean for
Yeah, it was
conventional
from
storage?
50 cents to $12.
Yeah, I think it depends on, so that wasn't just Sleipner, that's a range of potential projects. I think that was the IPCC estimate in their 2005 carbon storage volume. But so I think there's a lot of variability in, I think that includes transport, so how far you have to transport it, the cost of pressurizing the CO2. Yeah, it does seem like quite a range. Yeah.
I guess more of a comment. In California, in the Coast Ranges, the ophiolites are incredibly broken up. They're not ideal like the Oman one where you see these incredible zones and they're in place. And I could see that being a real issue in trying to find a place in the Coast Ranges. But if you go to the Klamath, you have much wider spread ophiolite, less people around, and especially the Trinity ophiolite, and then the Josephine also in the northwestern portion. That it could be an easier target and not as broken up as some of these other things are.
Good to know. Are there any student questions before I call it on? Yeah.
Are there other rock types besides ophiolites that would be a viable option? Or rather, like, what was it again about the ophiolites that made them so good for this opportunity?
So there's a couple things. There are other rock types, but the olivine reacts very quickly because it's out of equilibrium, and it has a high ratio of magnesium to other stuff in the mineral. So there's not as much silica and oxygen and other random stuff in there that you don't need for carbonation. So it takes less of the mineral in order to carbonate the same amount of CO2.
Okay.
So for 1 kilogram of olivine, you could sequester 0.6 kilograms of CO2. But so other rock types are, like basalt is being looked at. So blastonite is another mineral that they've looked at. Serpentine also, although serpentine is just a little slower in reactivity. And so then people have looked at, doing thermal activation to make it react faster, but then that takes additional energy. But so I would say basalt is the other big one that people are looking at. So places like the Columbia River basalts, there's actually a Department of Energy project investigating CO2, like a pilot project looking at CO2 injection into the Columbia River flood basalts. The other nice thing about basalts is you get a flood basalt, the middle of the layer is relatively massive, so low permeability and porosity, but the top and the bottom are all chewed up, so they have higher porosity and permeability. So if you inject into those layers in between the flows, the top and the bottom have high porosity and permeability, and then you've got a cap on top from the middle of the layer. Then you've got high porosity permeability and a cap on top. So it's got its own cap rock built in. And basaltic glass also reacts relatively quickly. So it's another good option.
All right. Well, thank you very much. That was excellent. Oh, did you have a
You have to
question?
wait, Don.
Well, no, I was just thinking instantly, I was thinking, has anybody ever looked at the concept of manufacturing these types of sites on a much smaller scale so it becomes part of the integrated operation of a facility? So you don't have to worry about the logistics of getting either one to the other place?
So manufacturing
An environment like you've described here, on a much smaller scale that could be engineered for a specific facility.
so they've
Then
looked
you
at
can start your own limestone farm.
right. So they've looked at that for the ex situ carbonation, where
Yes.
you then have to mine the rock and take it and grind it and pressurize it, and then it's economics, whether or not it's feasible to put in that much energy to bring the rock to the CO2 plant.
And has anybody ever looked at some of the, I'm thinking of the Washington and Denver fields in West Texas where they're injecting enormous amounts of CO2 for EOR. Has anybody looked at the side effects of what's going into that CO2? I know in the Washington it hasn't broke through. I don't know about Denver City, and they've been doing it now for, what, 25 or 30 years.
Yeah, so there are people looking at using EOR as a method for, this is enhanced oil recovery using CO2, used as a method of storing CO2. So instead of, right now the oil companies try to recover as much CO2 as they can so they can, because they don't have to buy more of it the next time they inject. But you could potentially try to leave some of it down there. And there are people looking at that. There are also people looking at, kind of getting back to your first question, old nickel mines already have peridotite that is chewed up by the mining process that they use to extract nickel. And then if you flowed water through those mine tailings, you could potentially form carbonate minerals there without having to, on a small scale for the mine, you could potentially offset your emissions.
You know, this was very fascinating. I learned a lot. But your second slide blew my mind. China. China is the second lowest, and it's only one that was lower one was the world.
Yeah.
Whereas, and it's probably part of that number being the world. You know, and you can just imagine when they get to a point that's going to go straight up in the air.
Yeah.
But
All right,
we'll stop
thanks.
it.
Thanks, everybody.